So thanks very much for the invitation. And so in this talk, I try to do two things. I'll explain this new result we have with Thomas Lamb. And at the same time, I'll explain a little bit informally how one can relate number theory, which is my field, to mirror symmetry. So there will be this kind of two kind of discussions. So I start directly with something which is familiar in number theory, and I'll explain then how it connects. So it's something called a Klosterman sum. You pick a prime P, and you have a finite field Fp. You pick another integer n, and then you make this finite sum. So it's sum over n minus 1 tuple of non-zero element in your finite field. That's x1 to xn minus 1. Then you have this exponential 2 pi I over p. So this creates a p's root of unity. And then this Laurent polynomial, which is x1 plus xn minus 1 plus 1 over x1 xn minus 1. So each term is a p's root of unity. You have roughly p to the power n minus 1 terms. And a very classical and very important result due to Deligne is that the size of this sum is actually the square root of the number of terms, roughly. So precisely, it's at most n times prime to n minus 1 over 2. So for n equals 2, it's Weyl bound. And sometimes we refer to it as analogous to the Riemann hypothesis over finite fields. But it's a theorem of Deligne. So any question about this object? So this will be kind of a main player in the talk. So
what is the motivation to look at this sum?
The motivation? Yeah, that's in fact, next slide I'm going to give some, perfect. So I waited for the question. So if you, let me give you some kind of motivation for where it came from briefly, so you have an idea of. So in fact, it was first defined by Poincaré in 1912 for n equals 2. But the first time it was really applied to solve a problem was by Klosterman. In 1926, he solved a question which is which integer can be represented as sum of 4 squares, maybe with coefficients. And that was important. And in fact, nowadays there is something called the circle method of R.D. Littlewood, and refined by Klosterman. So it's known as Klosterman refinement of circle method. So Weyl bound with what in the previous slide was for n equals 2. So then you get 2 square root p. That was proved in 48. And Deligne, so in 1975, proved this bound. That's in SGA. He has a very nice chapter of SGA where he proves this. And then it's still very active now. So Katz has developed the L-adic machinery much further and understood the monodromy, that it's a rigid local system. Then there is this work, which is essentially an extension of Poincaré's calculation to GLN. There is a geometric understanding by NGO. And so most important for me would be this latest development 2010, that you can think about this object as attached to GLN. And very recently, it's been generalized to other groups by these 3 people, Heinloss and Go-Yun. Actually, I did this work at the Institute in 2010 when I was also a member at that time. So, Okay, so that's backward. But let's come back to this object. So it's just a complex number which has a certain size. And so to make the connection more clear, I need to tell you the exact result and refine properties we know about these sums. So the exact theorem, it tells you that for any A, so before it was 1, but you can replace this by A, and in fact, it's the same as a Q in this superpotential. So yeah, so things as A as Q. It's not too far as a later. So the limit proves that this complex number is a sum of n Veil integers of weight n minus 1. So integer in the sense of algebraic integers. And the weight means the complex absolute value, in fact, of all its conjugate is p to the n minus 1 over 2. So this is a precise version of the bound, because you have n terms of this size. So that's a complex absolute values. It's also interesting to look at p-adic absolute value. That's due to Sperber and Daching 1, and also Dwork for n equals 2. Which says that this Veil integer, so Vp is a p-adic valuation. So equivalently, you can take the p-adic absolute value. You can arrange so that in order, it's also called the slopes, are 0, 1, 2, all the way through n minus 1. Yeah. And so as I said at the beginning, the proof of this is deep and the cornerstone of the theory of exponential sums. Yeah. So does the statement make sense? Yeah. Yeah. So now what I'm going to do is I'm going to interpret. So it's a bit of a heuristic because there is no exact homological theory that tells you you're allowed to do that. But I'm going to put these numbers in kind of a Roche diamond. So this I will call the Roche numbers for these Klosterman sums. And let's take n equals 3 to make a picture. So I have 3 numbers, alpha 1, alpha 2, alpha 3, and they're of weight 2. So it's natural to put them in the middle here if you think as horizontal lines as weights. So it's weight 0, 1, 2, 3, 4, and I put them in the middle. And their slopes, which is the other theorem of Sperber and 1, are 0, 1, 2. So it's natural to put them also, if you think as slopes, as filtration in this direction, to put them as 1, 1, 1 in the middle. Right, okay, so we do this from that. And then you flip the diamond, you get this diamond. And here you recognize some familiar thing. It's the cohomology of P2. So it's generated by hyperplane class, and so that's a Roche diamond of P2. Yeah, and then you look at, then it's well known in the mirror symmetry literature that the mirror of P2 is indeed this Laurent polynomial. So then it seems to fit well. So that's kind of a first observation here. So when you do this, this purity theorem of the line, which is everything has the same weight, corresponds in that side to say that everything is PP, like in algebraic in the middle, PP cohomology. So it's called Roche state type. And the slopes here, which are difficult to compute, correspond to the different degrees in cohomology. Yeah. Okay, so that's first example. Yeah, so now let's push this a little bit further. So these Klosterman sums were defined over finite fields, the FP. So yeah, there is a well-known analogy between sums and integrals and differential equation and L-adic shifts, and from Klosterman you get Bessel. So let me explain this. So one side to remind you of what's a Bessel function. So you take this differential operator, and basically Bessel functions are solution of this linear matrix ODE. So you can make it a scalar ODE, which is probably what Bessel did. And then it's rank 2. There are 2 linear independent solutions. I naught is well behaved at 0 in terms. There is a Taylor expansion like this. You can find them in terms of Frobenius method. And Bessel also proves the integral representation for I and K Bessel, which looks like this, which is the same phase as you saw before for Klosterman sums. So Yeah, this makes the analogy clear. So and here too there is a mirror interpretation, which is probably well known to most of you here. So that yeah. So in the previous talk we saw exactly the Gelfand-Setlin patterns and the superpotential. And so that's the case for CP1. So and for this the most simplest Grassmannian. Then you get indeed this superpotential. And then so the integral representation by Bessel is a special case of some mirror expectation. Then. Yeah, so that's another example to keep in mind for the talk. Yeah, so it's good to keep in mind this analogy. Oh yeah, so to not forget the analogy. So maybe that's the first idea is that this theory of Landau-Ginzburg model is there is a striking parallel with exponential sums in number theory. So I think it's a good guidelines to keep in mind for the talk, and this helped me. So this analogy is not completely new. If you read the article by Kontsevich-Solberman, at some point there is one section where they mention it. It's not been developed much as far as I know since then. It was in the mid-2006 or something. But at least on the surface, you have the same kind of data. Landau-Ginzburg model, you have some variety and a regular function on it. And in number theory, what people classically do is also they have some variety defined over Fp, a function on it, and then they take the exponential sum. Yeah, so that's the first idea, and so I'm going to push this idea further and connect it to the Langlands program soon. Yeah. Yeah, so when you do this analogy, immediately there is also something, other field that comes out, is that you can deform things in a family. So for instance, you may have this field of formal, so it's a puncture formal disk with deform C, and over Fp. In fact, for Fp there are two ways to deform. So one way is this one, which is geometric close to that one, and there is also another way, which is QP, and so this one I mention it because in number theory we struggle quite a lot with QP. So it's more difficult than this one because it's called mixed characteristic. It's characteristic 0, but the residual field has characteristic P. And there are lots of problems with QP. So people have invented methods to sometimes transfer problems from characteristic 0 to characteristic P. And so there is a whole lot of things going on in this triangle here. Yeah, but so if you're a geometer, you're a bit worried about all these finite fields. Let me say that it was just a motivation, like analogy. And then, in fact, for the proof and for the talk, you could just focus on just that part of the diagram, and this makes sense. So, yeah. Okay, so now I will explain what the theorem is more precisely, and so that was more kind of a motivation. Yeah, so that's the flavor of mirror symmetry I'm aiming at. So it's the case of when you have a Fano type mirror pair, and from you look at the smooth projective Fano as the A side, and you extract this quantum differential equation. And small means you restrict to quantum multiplication by H2. And on the B side, you have this Landau-Ginzburg model, and from this I'm going to extract this integral, which we're going to. I want to view it as a D module. Yeah, and then so the mirror type question I look at is that these two, if you have a Fano mirror pair, well, these two are expected to be isomorphic objects. So that's the kind of result I'm looking at. Yeah. And specifically, I'm going to look at it for Grassmannians, and more generally some homogeneous projective spaces. So this is a slide to remind you of Grassmannians, but the previous talk was about Grassmannians, and so yeah, so you've already seen this in much more generality. So I'm going to use Plucker coordinates too, and yeah, so you've seen this before. And yeah, so flag manifolds appear in many different. Maybe I should not slide this. Okay. I'm careful. And so in lead theory, it's important. Yeah, so algebraic geometry and combinatorics, and there is a Borel-Weilbot theorem. And in number theory, it appears often when you look at Shimura varieties and you look at the boundary of these complicated varieties, they look like flag varieties. So that's one motivation. Yeah, so let me tell you what the theorem is now. Yeah, if you take one of these flag variety, and I make the assumption that it's minuscule. So if you don't know what's minuscule, there is a complete list here of the minuscule flag variety. So yeah, I'm going to explain the thing. And if you're afraid of Lie groups, you can just focus on Grassmannian. For Grassmannian, it's already highly interesting. And in fact, the result is new for Grassmannian. So yeah, if you don't like Lie groups, just look at Grassmannian. So if you like Lie groups and you like exceptional Lie groups, we can do E7, the case of E7, in which case you have the G mod P is a Freudenthal variety. So okay, so start from one of these flag manifold, and you view it as a A side, and so and on the B side there is a mirror, and you do this push forward D module, and yeah, and so we prove that there is an isomorphism between the two. So that's what the main statement is. So yeah, what's the variable here? The quantum variable A. So because it's minuscule, H2 has dimension 1, because minuscule implies maximal. And so this is an ODE, linear ODE in one variable. And here you also have one variable A, and yeah, and so so terms that we identify these two objects. So it applies to minuscule flag varieties, which includes Grassmannians, even dimensional quadrics, the spinor variety. So yeah, so this is a Dynkin diagram, and the mark here, each node corresponds to a maximal parabolic. It tells you which parabolic I choose. So for Grassmannian, I can take anything in this line, and here it's this vertex. These two are the same. That's E6, you take this one or that one, and E7, it's that one. Yeah, so for E6, you get projective octonions, which were. So it's mirror symmetry for this kind of variety. Yeah. Yeah. So the context is that it was conjecture by Rich. And she constructed exactly this mirror and the superpotential, so as we've seen in the previous talk. So in the previous slide I have this check, but we saw this Langlands dual notation in this morning by written. So it's the same Langlands dual check. So if it's simply laced, then G check is essentially the same as G. You can ignore the check. So in fact, here I gave you all the simply laced cases. So yeah, you could ignore the check if you want. For that you wouldn't lose anything. So yeah, you have G and the parabolic, and Right. So the mirror here, it's this open projective Richardson, where you take this projective G mod P and you remove one anti-canonical divisor. Yeah. So this conjecture by Rich emerged as it's kind of remarkable that it emerged as a combination of various things. One from crystals, like from Lustig, Zelevinsky, Fomin. Again, we've seen that in the previous talk. If you tropicalize this, you get the theory of crystals, like in Lustig, Kashiwara. Also, the work by Peterson and quantum Schubert calculus on that side, and also Witten, Waffa, and others on Landau-Ginzburg models for Grassmannians. Okay, and the new input in our work with Lam is that we approach this using automorphic forms. So that's the other idea I want to explain next. Yeah, that's all. Any question about the statement and the context? Yeah. Okay, so it's a bit more formally what's. So if you're a geometer and you want to know what's inside this G mod P circle F. So the exact definition is you have this Weil group attached to the levy. You fix the opposite Borel, some additive character, and then you do this kind of intersection. So it's a bit like a double Brua cell. You take a B minus, the opposite Borel, and you intersect with a U double cell with this WP element, whose inverse is longest element. So a little bit of roots combinatorics. And then this double Brua cell is the main player here. And then the potential in this intersection has a very nice form. It's given by psi of the first U variable and psi of the second U variable. So if you think of GLN, psi is like adding all the variable in the of the diagonal, the first off diagonal. So you extract your first diagonal, you add all the coordinates. And you do this once for U1, once for U2. And that's the superpotential. And so that's what, so that's a remarkable recipe of Rich. And also Berenstein cache down, so I call it Berenstein cache down geometric crystal because independently and for completely different reasons, they had a similar construction around 2000. Yeah. Okay, and geometrically, this intersection lives inside G, but in fact, you can mod out by B because it's in the big cell of G mod B. And then you can project from G mod B to G mod P, and it turns out to be an isomorphism onto its image, and you get an open dense subvariety of G mod P. So it's worked out in this paper by Knudsen, Lam, Speyer. Yeah, so that's kind of the underlying geometry. Yeah, and then how do you construct? So F is a potential, and then the base is this the center of the levy, which is this where this A live, which is one-dimensional.
What do you mean the base? The base of what?
Yeah, so in this theorem, you identify the H2 on the A side, with the base of the deformation on the B side. And so here we see the base of deformation on the B side is the center of the levy.
So I should think this is a family of potentials.
Yes, that's why. So there is always this F sub A,
Okay.
which yeah. So things depends on A on the base. Yeah. Yeah. So a little bit more geometric facts on this. So it's a log Calabi-Yau when you do this because you removed an anti-canonical divisor in the Fano. So it's a very nice divisor. It's a union of Schubert divisors. So there is a volume form. So it's also a cluster algebra. So it's also a wild character variety if you like character varieties. And yeah, and if you like to make mirror symmetry more symmetric, so the Rich conjecture was from 2008. You can, because when you write it this way, one side is a Fano and the other side is like one Landau-Ginzburg, you might worry about where the divisor is. And it's possible to make it more symmetric now, where the expectation is probably that you put anti-canonical divisor on the on one side and the potential also, and the same thing on the other side. Yeah. So maybe simplest example is P2. So to be sure everybody on the same page, what you remove is union of 3 lines, and so the volume form is dx0, dx1, dx2 divided by x0, x1, x2 and on the projective coordinates. Yeah, and so you have this well-known Landau-Ginzburg model with this. So there are 9 indeterminacy at infinity. The fibers are like elliptic curves. And yeah, so that's the P2 mirror, which is probably well known to most people. Right, and so that's the context where we prove this. Right, so to put in context, so projective space is like this base example. So for P2, there is this famous result of Kontsevich that you probably know, counting curves of degree d through 3d minus 1 points. Yeah, and since the 90s, we want to generalize it. So there are lots of works, including Denis Aurou's talk on Monday on toric case. And so this talk is in the direction of going to projective homological varieties. So you replace Pn by some other G mod P. And maybe in Europe, there is a large program of looking at low-dimensional Fano varieties, like del Pezzo, 3 folds, 4 folds, and so on. OK. Yeah, so one example to see exactly what the theorem means. So I take the, yeah, so in fact, I remove the background where it came from. So it becomes an exercise in calculus. You could say it doesn't come from, you could forget the context, just give this to someone and ask to check what the prediction is. So, yeah, and then I did the exercise for you. So. Yeah, so you just give someone, say, this linear ODE, which is given by this 6x6 matrix. And then there is this function, which given by this Laurent polynomial. And you integrate, say, over this compact half-dimensional cycle, so over product of S1s. You get this I function. And the claim is that this is a solution of this. So like in Bessel, you could ask Bessel if you were alive to check. Bessel did it for 2x2 matrix, essentially, and can you do it for this 6x6 matrix? That's the question. And so a way to solve this exercise is to, you can expand this by Cauchy residue theorem. In fact, it's an hypergeometric type function. And then by hand, you can cook up a scalar differential operator that annihilates this. It's kind of binomial identities. So actually, this is non-trivial, actually, this binomial identity. So because it's low dimensional, you can write it explicitly. And then you want to pass from the scalar ODE to the matrix ODE, which is an exercise in algebra. But it's also non-trivial, because why should it be exactly these numbers here that correspond to this matrix? Yeah, so that's kind of one part of the theorem. It tells you that you get solutions of the ODE. Another part of the theorem, in fact, it's a bit stronger, and that's a new feature for Grassmannian, is that we get all solutions this way. That's more difficult to prove. That if you integrate over different cycles, which, in fact, you can take them as, you get all solutions of this ODE. Yeah, and this we get as a nice byproduct of all the work we did to embed into the Lagrange program, because in fact that's one of the facts that Lagrange program gives you, that you get this this kind of fact. Yeah, and so here I add where it came from. So it's really what the mirror theorem predicts, because this is a quantum differential equation for this quadric, which is a Klein quadric for Greux 2-4. And this is really the superpotential for restricted to this cluster chart for the Grassmannian.
So
Question?
when
Yeah.
you represent the solution by integral, what kind of cycle do you do?
Right. So here for this one, I use a compact cycle, like product of S1s, and that's why I can apply Cauchy residue. But in fact, that's exactly why I'm going to use the language of D modules. This is the next slide. Oh yeah, perfect. Yeah, it's good. You always predict my next slide. So that's exactly why I'm going to use D modules, because this D module is exactly the language which enables you to talk about differential equation and integral without choosing a cycle. Basically, tell you. So you can say I take this integral, and this I call it a push forward, and that's a D module without choosing a particular cycle. So that's very convenient, partly for this. Yeah. So let me introduce this language of D modules if you're not familiar with it. So as I said, my talk, everything is ODE one-dimensional. So A is this one-dimensional variable, so it's this coordinate on GM. And the structure sheaf is this, and then you have the, you want to study differential operators, so you have the, you introduce the Val algebra, and which is non-commutative with this commutation relation. So we've seen the scalar ODEs and matrix ODEs, and so in fact the matrix ODE is the same as a vector bundle with a connection. And it's also the same as a D module, which is O3. So because the O3 module is a vector bundle, and the D module structure exactly gives you a connection. Right. And so in each case, you can consider solutions. So here you would solve LU equals 0. Here you would take flat sections, and here you take a Hom. So in D modules, Hom correspond to solutions. Okay. Yeah, and so example are like hypergeometric equation is one case, and so you get this differential operator, and so this includes exponential powers, Bessel functions, Kummer confluent hypergeometric, the Gauss hypergeometric function, and so on. Yeah, right. So I use this language here on the right to say that I push forward, which means I integrate to get a D module. Yeah. So if you're familiar with Gauss-Manin connection, it's the same as considering theorem homology of this. And so part of the theorem is that on the left you have an integrable connection, so which is everything is in 1 degree, whereas on the right it's not it's not at all clear that you should get the theorem homology is in 1 degree. So I come back to this proving. So that's part of the theorem. Yeah. So maybe as an outsider, I try to understand mirror symmetry. There is a B side and the A side. And maybe the A side you cannot compute, and the B side is complex geometry. You cannot. It's difficult to understand complex geometry. It's mysterious, but still the two are related. And yeah. And so in that, with the addition here, I add automorphic forms to the mix. And automorphic form, that means there is many people. There is a computational aspect, which is very interesting. It's challenging to compute, and also so you can half compute, half understand. Yeah, so now, in fact, yeah, so that's kind of, I want to tell you a bit about how the proof goes, because there are a few interesting features, I hope there, and that gives some hints of what to do in other cases too. Yeah, so there is a key object that will relate the two sides. And this key object, in fact, has been constructed by Dick Gross. It's kind of a remarkable object, which is attached to any complex reductive group. And he constructed, so it's very universal kind of construction. He constructed some automorphic form, which in a sense is like the simplest possible automorphic form for this group G. So in the sense that it has very little ramification. So maybe not many of you are familiar with automorphic forms, so we'll try to keep the language minimal on that aspect. But so it lives on P1, more precisely bungee of P1, and it's ramified at exactly 2 points. 0, where it's tame, and infinitely, where it's wild. But in fact, they use the word simple supercuspidal, which means it's the simplest possible, the lowest possible ramification you can put for this. Yeah, so about 10 years ago, so Gross found this automorphic form, which lives on P1. And it's unique, so it's really characterized by this property. So probably you've already heard of Gauss hypergeometric function and Riemann's reinterpretation of it via monodromy. So if you know this, it's very similar. So the Gauss 2F1 hypergeometric, it's ramified at 0, 1, infinity, and it's characterized by its monodromy at each point, which is semi-simple. And in fact, Riemann introduced even a notation for this. So it's F, and you have this. So you probably have seen this notation before. And then you have 0, 1, infinity, and then some numbers, alpha, beta. And yeah, so it's the same, but generalized to a general group, in a sense. So it's a fundamental object, and it's striking that it's been found only about 10 years ago by Dick Gross. Yeah, and so again, maybe another quote to get oriented is, yeah, so it's the kind of simplest possible object. So before Gross, in many cases, it was constructed by Katz, at least the Galois version. Yeah. Yeah, and so the next, so I mentioned at the beginning that there is this work of Heinloss and Goyun, where they have a more direct construction of this automorphic form AG, which is a constructive version. And so that's what I'm going to use for the proof. So okay, this might not tell you too much if you don't already know the work of Poincaré and Poincaré series, but it's kind of analogous of a Poincaré series, if you've seen this for SL2Z. Yeah, so there is an interesting history that it appeared in last paper of Poincaré in 1912, a few days before he died. So that's the paper, in fact, where I introduced Klosterman sums. Yeah. Okay, so yeah, so this object, which is maybe a bit mysterious, will be kind of the main tool. So here is kind of schematically what the proof looks like. So we want to relate the A side and the B side. Well, that's the goal. And we do that in 2 steps by relating to this object in the middle. Yeah. So this horizontal line is what we are after. And the way we do it, we prove two things. One is this arrow, and the other is that arrow. So here you have an ODE. And so it turns out that the geometric Lagrange program, there is so one of the cornerstone is something called Lagrange reciprocity, which tells you exactly that linear ODE correspond to automorphic forms. So I'll explain in the next slides if you probably haven't seen it. I mean, it takes a long time to define what's Lagrange reciprocity, what's the exact conjecture is. But I will give you a flavor in the next slide. Yeah. So one step is to relate this quantum differential equation, which we saw before, for instance, for the Klein quadric, to relate to here. And so here we are helped also by a theorem of Zhu, recent theorem of Zhu, which did exactly that case. Because in fact, it's kind of still quite open, active program to prove Lagrange reciprocity for geometric version in more cases. As of today, in the wild case, in the ramified case, it's not quite. There are lots of work to do. And you might have heard talk. I mean, other people in the unramified case, which is already challenging, and there have been lots of progress. So here it's a ramified case, which is even more challenging. So yeah, so there is this bridge here that we do. And then we do that on the other side. So you have this automorphic form, and you want to relate to the Landau-Ginzburg model. And so here, in fact, so it's also a bit technical to explain, but the key is this Recke eigenvalues or Recke modifications. So this morning we had this talk by Ritten, where he explains what the Recke modification was in various examples. And if you remember, he had this CP1 coming out for SL2. And CP1 is one of these G mod P, so GL2 mod P1. So in fact, this is realized inside the Recke correspondence, inside the Recke modification. So this morning we had this moduli space M, where things took place, and it's kind of the same space here that appears. This Recke modification. Yeah, and so after lots of manipulations, it turns out that you get exactly the Landau-Ginzburg model of Rich. Yeah. So yeah, so here we kind of relate mirror symmetry with Lagrange's program, and it's been done before. Especially there is this paper by Ritten, gauge theory and wild ramification. But we do it in quite a different way, so it's not clear exactly how the two stories connect. Yeah, so okay, in the next, so that was overview of the proof. So in the next few slides, I want to explain to you a little bit more the flavor of what's behind this reciprocity, and also give you some hint of why it fits more generally, things more generally. Yeah, so one naive way to enter these questions, and it's a way that I like, is to think that you want to solve ODEs. Because once you've stripped out this mirror conjecture out of all the context and you just focus on just the ODE and the integral, well, there is not that much left. You just have one integral like this and one ODE. So what can you do with just this basic building block by just solving ODE? And yeah, so one observation is that that's the output of this mirror expectation. Yeah, and the other observation is that it's also an output of Lagrange reciprocity. So in fact, the reciprocity conjecture says that essentially you can solve any linear ODE by a Recke integral. That's one informal way to state it. But it's not far from the from true. And with some work, you can make it actually. There is you can make it a theorem, for instance. There is a theorem that L-adic sheaves are motivic, for instance, which is a very strong theorem proved about 15 years ago. And so it's a very deep aspect of the Lagrange program that there are these ODEs behind. And so one way to connect the two, which is what we did, is to just connect it via these ODEs. Because if they solve the same problem, maybe they are related. Yeah. So that's kind of maybe the second idea. Yeah, so in mirror symmetry, you always have the generating series given by exponential of superpotential, maybe of counting curves and so on. Yeah, and to give you an idea of what's reciprocity, let me tell you what Gauss reciprocity is, if you haven't seen it before. So it says that a prime Q is a square mod 5 if and only if 5 is a square mod Q. So it was one of Gauss' favorite theorem, and he came back to it many times, giving different proofs. So it's very useful in practice. So suppose Q is this prime, which is the largest non-prime, according to Wikipedia. Well, I can tell you it's a square mod 5. I would have some difficulties to give you the square root just on top of my head. But if I apply Gauss reciprocity, I have to check. I just have to check that this number, this exponent, is 81, which is 1 mod 4, and 2 to the 4 is 1 mod 5. So the last digit of Q is 1, and that's enough to tell me that Q is a square mod 5. Yeah. Okay, and maybe you're going to tell me that Gauss reciprocity has nothing to do with integrals. But in fact, Gauss introduced Gauss sums, and he computed the sign of Gauss sums, and it's essentially it's a sum instead of being an integral. But it looks you can think about it analogous to the gamma function, and then the Gauss reciprocity tells you that this Gauss sum is equal to square root 5 if 5 is a square mod Q, and minus square root 5 is if 5 is not a square mod Q. That's roughly equivalent to the Gauss reciprocity. And yeah, you can think about this as analogous to Recurre integral, which is technical to define. Yeah. Yeah, and then so this quantum Q, I view it as analogous as this prime Q. So that's why. So here you have generating series, and here you compute sums, arithmetic quantities. Yeah, that's. So this would be essentially for the group GL1, if you want. What happens for GL1? Yeah, and so this is what goes into essentially that black box and this black box for general. Yeah, so I have about 10 minutes left or something.
Yeah.
So, yeah, any question about this? Yeah, so maybe this is how I got interested in mirror symmetry in the first place, because I was looking for this integral representation are very important in number theory. Maybe I've said it maybe already, but I mean we need those. There's also something I would call Gelfand program, where you study spatial functions, and I like this too. And in representation theory, we also have this kind of integral sum, like Jacquet integral, which shows up, and exponential sum. So yeah, these objects show up, and it turns out that sometimes they match things constructed like a Landau-Ginzburg model or in mirror symmetry. Yeah, okay, and so to give you some, yeah, I mean, solving ODEs it looks a bit simple, but in a sense, it underlies many developments in history. So, yeah, so let's not spend too much time on that. Yeah, maybe to finish, I'll explain maybe in a bit more detail what the theorem says and what it implies. So, for these minuscule cases, so with some work, you can take the semi-classical limit of taking h bar goes to 0. And then you recover so another mirror expectation, which is that the quantum cohomology ring is a Jacobian ring of the superpotential. So in fact, Constance Rich proved that this Jacobian ring is the same as a Peterson variety introduced by Peterson. And so she also proves this for Grassmannians and also other flag varieties. And this, which we interpret as a mirror prediction now, was also announced by Peterson in 1997. So you can get this result as h bar goes to 0 limit, semi-classical limit of the other mirror theorem. Yeah, so like a homological consequence also, I hinted it before, that if you take this Landau-Ginzburg model, you take Durham cohomology. So it's a Durham cohomology of this integrable connection with these twisted coefficients. So what it means is you take all the differentials times exponential modulo exact differentials, like you would do in usual Durham cohomology, but with exponential f. Or if you want, you take this the complex with this differential. So you can compute it for P1, for instance, for an example. But so the consequence is that this is 0 except in degree d. So that's what this d module, push forward d module means. And also in degree d, it has a right dimension. So it's same dimension as the cohomology, total cohomology of the mirror. Yeah, I don't have time to explain, but on this side, once you interpret into the Langlands program, it's natural. It's essentially the Ramanujan bound or Ramanujan conjecture, which is another big cornerstone of the Langlands program. So that's why I like this connection, because it connects difficult thing on mirror symmetry with also difficult thing in the Langlands program. Yeah. Right, and if you want to go deeper, like if you want Hodge properties, this side also has a filtration, so an irregular filtration. So recently there have been a couple of papers on this theme. So it's nowadays sometimes called the Deligne filtration. And so one way to construct it is via the Konchevich complex. And so because on the left you have a graded ring, and so on the right you want to see the reflection, the mirror of the grading, and so you don't quite have a grading, you have just a filtration, but the expectation is that they correspond. Yeah, and this essentially is what I started with in the first slide, the Deligne's theorem and Sperber theorem, that the weights for the Klosterman sum are like this Hodge diamond on the right, and they are mirror to the Hodge diamond for CP2. Yeah, I'd love to make this into a proof, and I've talked to some people about how to proceed, but with homology, yeah, so this is a workshop on homological mirror symmetry. This would definitely help towards this. But right now it's more heuristic than. Yes. So maybe a challenge for the audience will be to have a symplectic proof of the Deligne theorem. Yeah, that would be lovely. Yeah. yeah, I love to do that. Yeah, maybe so to finish the talk, yeah, let me explain. So I use the fact that it's a rigid object. So like this 2F1 Riemann-Gauss hypergeometric, which means the object is pinpoint by its monodromy at 2 points. It's a very beautiful property, but it's also a very spatial property. So you might want to extend more generally. And here is maybe one speculative side about what to do more generally. So if it's not rigid, what you have is essentially a family of objects. You have a family of ODEs which vary with parameter. And in number theory, we already have the technology to deal with families. It's yeah, it goes back a long way, and yeah, and in mirror symmetry, you also have the idea of Frobenius manifold, especially, which is an isomonodromy equation, which is very similar to here having a family in the Lagrange program, where you have things which are attached to the same group. Yeah, and I'm hopeful that this can be pushed further, especially because Lagrange functoriality conjecture tells you that all automorphic forms should live on GLN for some n over P1. So it's another big conjecture in the subject. And so by examining families of ODEs on P1, which is what these non-commutative Roth structures are, I hope there is a chance to match more cases. Yeah. And, yeah, so I think I will stop here. Thank you for your attention.